Air is everywhere. We breathe it without thinking about it. It surrounds us every second of the day, completely invisible. But in modern industry, air is not just something we live in. It's a raw material. Factories don't simply use air as it is. They take it apart, separate it, and transform it into something useful. Oxygen and nitrogen are extracted from the air we breathe and used in hospitals, factories, and advanced technology. And most people never realize how complex that process really is, or how important it is for the modern world. What makes this process so fascinating is how much precision is involved at every single step. What looks simple from the outside is actually the result of thousands of small adjustments happening at once. Temperature, pressure, timing, all of it has to be perfectly controlled. Even a difference of a few seconds or a slight change in heat can completely alter the final result. At this stage, machines are constantly monitored by sensors that track quality in real time. If something goes even slightly off, the system reacts immediately. This ensures consistency, not just for one item, but for millions produced every day. That level of reliability is what allows modern production to scale globally. What's interesting is that many of these techniques were developed decades ago and refined slowly over time. Engineers didn't reinvent the process overnight. They improved it step by step, learning from tiny failures and inefficiencies. Today, those lessons are built directly into the machines themselves. This is where technology quietly does most of the work, turning raw materials into something familiar, functional, and ready to be used, often without us ever thinking about how much effort went into creating it. As the process continues, the focus shifts from transformation to refinement. This is where efficiency meets precision. Each stage is designed not just to move materials forward, but to improve them in small, almost invisible ways. Surfaces become smoother, structures more stable, and tolerances tighter. What once looked rough and unfinished slowly turns into something reliable and repeatable. Modern production relies heavily on automation, but human expertise still plays a crucial role. Engineers and technicians design these systems with one goal in mind: reducing variation. The less variation there is, the more predictable the outcome becomes. And predictability is everything in large-scale manufacturing. Another key element here is speed. These machines are not only accurate, they are fast. Components move seamlessly from one station to the next, often in a continuous flow that never truly stops. Downtime is costly, so systems are built to run for hours, sometimes days, with minimal interruption. At the same time, quality control is happening constantly. Cameras, scanners, and sensors inspect products in real time, checking dimensions, alignment, and structural integrity. Anything that doesn't meet the standard is removed immediately. This prevents small issues from turning into large-scale problems later on. What's remarkable is how quiet and controlled this entire process appears. Despite the complexity and scale, everything runs with a calm, almost rhythmic motion. It's a balance between power and precision. Machines working at their limits, yet remaining perfectly synchronized. By this point, the product is no longer just a concept or a raw material. It's becoming something tangible, shaped by layers of engineering decisions made long before it ever entered the production line. At this stage, the process reaches its most critical phase. Everything that has happened before leads to this moment, where precision matters more than speed. Small adjustments here can make a significant difference in the final outcome. Temperatures, pressures, and timing are carefully controlled, often down to fractions that are invisible to the human eye. What makes this step especially important is consistency. Producing one perfect result is easy. Producing thousands that are all identical is the real challenge. That's why modern systems constantly compare real-time data against predefined benchmarks. If even the slightest deviation appears, the system reacts instantly, correcting itself before errors can spread. Energy efficiency also becomes a priority in this phase. Machines are optimized to use only what's necessary, reducing waste and heat loss wherever possible. This not only lowers costs, but also minimizes environmental impact. An increasingly important factor in modern manufacturing. Behind the scenes, advanced software coordinates every movement. Each machine communicates with the next, forming a network that behaves almost like a single organism. When one part slows down, others adjust automatically to maintain balance across the entire line. By now, the product has passed through countless checks and refinements. What started as raw material has been transformed through controlled force, precise engineering, and intelligent automation. It's no longer just about making something work, it's about making it work flawlessly again and again. As the process continues, the focus gradually shifts from transformation to verification. By this point, the product may already look finished to an untrained eye, but in reality, it still has to prove itself. This is where reliability is tested, not just appearance. Every unit is examined to ensure it meets the same standards as the one before it. Sensors scan surfaces, measure dimensions, and detect imperfections that are impossible to see without specialized equipment. Some systems use high-speed cameras, others rely on lasers or pressure testing, depending on what matters most for the final use. The goal is simple: eliminate uncertainty. Nothing moves forward unless it passes every check. What's remarkable is how fast this happens. Decisions that once required human judgment are now made in milliseconds. Algorithms compare each result against thousands of previous examples, learning over time what's acceptable and what isn't. This constant feedback loop improves accuracy with every cycle. At the same time, durability becomes a central concern. Products are often exposed to stress tests that simulate years of use in a matter of minutes. Heat, vibration, load, and repetition all play a role. If something fails here, it never reaches the next stage. That failure isn't wasted. It becomes data, feeding back into the system to prevent the same issue from happening again. There's also a human element behind all of this. Engineers and technicians monitor trends rather than individual units, looking for patterns that suggest long-term issues. A small change in performance today could indicate a larger problem tomorrow. Catching it early saves time, resources, and trust. By the end of this phase, the product has earned its place. It's no longer just something that was made. It's something that has been tested, challenged, and refined. What remains is the final preparation, where everything comes together before it reaches the world outside the factory. By the time this process is complete, the result feels almost effortless. Something invisible has been separated, refined, and prepared with incredible precision. Yet most of this work happens far away from everyday life, hidden inside industrial systems we rarely notice. What makes this process remarkable isn't just the technology involved, but the patience behind it. Cooling air to extreme temperatures, controlling pressure, and allowing physics to do the rest takes time and careful planning. Nothing here is rushed. Every step depends on stability and balance. Oxygen and nitrogen may seem ordinary, but without this process, modern medicine, manufacturing, and food preservation would look very different. These gases quietly support systems we rely on every day, without ever drawing attention to themselves. So the next time you see steam rising from an industrial plant, or hear about liquid nitrogen being used somewhere unexpected, remember this: behind something as simple as air lies a process shaped by cold, precision, and decades of engineering knowledge. Sometimes the most important materials are the ones we never see.